To lecture 20, it's, in some sense for me it's a leftover from lecture 19, but I think it's okay, good that we are dealing this Xyz theorem in a separate lecture, so I can do a slower build-up of the context of the theorem and do the proof in a bit more detailed fashion. Okay, so this Xyz theorem is a theorem on theorem about linear extension of partial orders. We will see what that is, but let's quickly recap. We are going to prove this Xyz theorem by applying the FKG inequality. Just quickly recall what was the FKG inequality in its quote-unquote memorable form. The FKG inequality says that if mu is a log supermodular probability distribution or a log supermodular PMF, probability mass function. In fact, I think that is more clear, right? I can just call it a log supermodular PMF on a finite distributive lattice L, and f and g are both increasing functions, increasing real valued functions. Okay, initially when we proved, we had the restriction that these are functions to non-negative real numbers, but we saw how to remove that restriction. So if f and g are any two increasing functions, then we say that f and g are positively correlated, which means the expectation under mu of the product function fg is lower bounded by the product of the expectations. We are going to use this in a very, very clever way in proving a theorem about linear extensions of partial orders. So partial orders, I know every one of us knows, plus we had also recapped it when we were defining lattices. And what is a linear extension of partial orders? A linear extension, so given a partial order P with this some precedence relation, which I denote by this precedence symbol subscript P, a linear extension is a total order. Remember, a total order is a partial order in which every two elements are comparable. Okay, so your divisibility relation is usually not a total order because neither 2 divides 3 nor 3 divides 2, so it's incomparable. Whereas a less than or equal to relation is a total order because any two elements are comparable under this relation. Either x would be less than or equal to y, or y would be less than or equal to x. Okay, so that's the definition of a total order. It's a partial order in which every pair of members is comparable. For every x comma y, either x less than or equal to x precedes y or y precedes x. Now, a linear extension is a total order on the same domain of P. So remember, notice here that it is the same P here and here, but plus with the additional demand that this total order respects P. Okay, so what do we mean by one order respecting the other? That means that everything that is related in a particular way under P is also related in the same way under the new order, this under this T. Okay, so formally it says that if x precedes y in this partial order P precedes P, then x should precede y also in the total order. Such total orders are what are called linear extensions of a partial order. Okay, so this condition tells you that T respects P, and the fact that T is a total order, by the way, the linear order is another name for total order, and that is why this name, linear extension. So the divisibility relation we just saw, is not a total order, but the usual less than or equal to turns out to be a total order, which is a linear extension of the divisibility order. Okay, you can pause and verify that. Now, does every partial order have a linear extension? Does it admit a linear extension? If it was finite partial orders, all the computer science students here would have studied this algorithm called topological sorting. So essentially the topological sorting works on a slightly more general setting of directed acyclic graphs, but posets are a special case of directed acyclic graphs where the extra requirement for a poset is that the underlying directed acyclic graph also has transitivity, right? So, but poset is a DAG, and hence topological sorting of that DAG would give a linear extension for any finite partial order. The linear extensions are not unique. In fact, counting the number of linear extensions of a given poset is a very interesting problem. Okay. By the way, there is this empty poset, or in some sense, you can take some n elements and say that none of them is comparable to each other. Like, for example, sets of the same size under subset relation. Okay, none of them will be comparable against each other. In this case, any permutation of the domain qualifies to be a linear extension. So there we know the count, the number of linear extensions which are for this poset would be n factorial. But once you have certain partial relations, the number of linear extensions is a very difficult quantity to estimate. Yeah, but what about infinite posets? We won't deal with that because anyway we are going to see apply this Xyz theorem is about finite partial orders, and hence we won't need the infinite case. But still, even in the infinite case, every partial order, even if P is in an infinite set, every partial order has a linear extension. But proving this requires an axiom of choice. Yeah, and this is the example that we were, say, consider the set 1, 2, 3, 6 under the divisibility relation. This is the Hasse diagram of that partial order. But there are two possible total orders which qualify to be linear extensions of this. 1, 2, 3, 6. This is nothing but the typical less than or equal to order. But 1, 3, 2, 6 also is a total order which is a linear extension of this. Okay, so yeah, the only thing that the total order has to respect are those elements which are related under P. Since 2 and 3 are unrelated or incomparable under P, the partial order is free to place them in, the total order, the linear extension is free to place them in any order. Okay, now we are ready to state the Xyz theorem. Okay, it was conjectured a year earlier by Ruval and proved by Lawrence Shepp in 1982. So let P with this precedent symbol denote a finite poset, and let this tau, I use tau to denote the set of all linear extensions of P, right? So in this case, tau would consist of both T1 and T2, okay? And if for larger partial orders with a lot of incomparable elements, this tau can be a very huge set, but still at most n factorial if n is the number of elements in P. Okay, but not all of n factorial as long as you have some order relations already inside P. Okay, so but anyway, tau is the set of all linear extensions of the given partial order P, and we consider this random experiment of picking a linear extension of P uniformly at random, or equivalently picking a member of the script T uniformly at random. Okay, so that is the random experiment that we are talking about. Okay, now the XYZ in the theorem comes because of this condition. You pick any three elements X, Y, and Z of P from P, and the XYZ theorem tells you that the join probability of the total order putting X before Y and putting X before Z. Okay, so this is equivalent to saying that the join probability that X precedes both Y and Z is greater than or equal to, is lower bounded by probability or the product of the probabilities of these individual events. Okay, so yeah, you should think of this something like probability of E1 intersection E2 greater than or equal to P of E1 P of E2. So in some sense this is like the the Kleitman kind of a relation. We are looking for a positive dependence among these two events. We want to show that E1 and E2 are positively dependent. What is E1? E1 is X preceding Y in the total order. E2 is X preceding Z in the total order. Okay, and XYZ theorem tells you that these two events are positively dependent. Okay, so XYZ theorem is equivalent to saying that E1 and E2 are positively dependent, where this is what I call as the event E1 and this is the event E2. Now actually this is obvious if, let us say, X was already preceding Y in the partial order P. Remember, this conclusion is about this linear extension chosen uniformly at random from all possible linear extensions of P. But suppose this X preceded Y in P itself, then in every linear extension T, X will precede Y. Hence this is sure event, so its probability is 1. Okay, and this is a sure event intersection another event, so this is just E2. Okay, in this case what we are saying is that E1 is the entire event, okay, or our sample space here is the script tau, right? E1 is the entire tau, so tau intersection E2 is just E2, and this is only saying that P of E2 greater than or equal to P of A2. So this is a obvious statement. The same holds true even if it was given that x preceded z in the partial order P itself. It's also easy to verify that this is true when y precedes P in z or z precedes y. If y and z were comparable in P, then also this is easy, because let's say y was before z, then if x precedes t in y, and since y anyway precedes z in P, it should precede z in t also. So y would precede z in t, and then by transitivity x would precede t. Okay. So in this case actually E1 will imply E2, or equivalently E1 is a subset of E2 if you think about Venn diagram. So this E1 intersection E2 hence is just the smaller one, which is E1, and here it is saying probability of E1 times another probability. So this is just saying that probability of E1 is greater than or equal to probability of E1 times another probability. Since this is a probability, this is also easy to verify. So there is nothing non-trivial about this statement. When any two of these x, y and z are already comparable in P, the non-trivial content of this statement is when these three guys are pairwise incomparable in P. But here also, actually, even if you do not do a course in probabilistic method or something, if you ask somebody who knows probability, like what is your intuition, they'll say that, yeah, this looks like they are positively dependent, because by placing x before y, you only look like you are improving the chances that x is also before z. Okay, because x is before somebody means x is probably earlier in the total order, and hence it has more chances of preceding z also. So conditionally it looks like, by the way, this intersection probability, you can equivalently talk in terms of conditional probability. We have seen that many times, right? This is equivalent to saying P of E1 given E2 is greater than the unconditional probability of E1. Okay, so that intuition seems to hold, and that is why 1 year before Rival had conjectured it, but this was notoriously difficult to prove. Okay, though intuitively it looked clear, it was very difficult to prove. And again, the proof that we will see today is quite clever. Okay, it's quite a clever application of already a non-trivial result, a clever result like the FKG inequality. Okay, so yeah, this I have already mentioned, that was conjectured 1 year earlier. No? Typically, when something is left out as a conjecture, that means that the person who conjectured it tried to prove that quite hard and failed. Okay, so that is why proving a conjecture is considered quite valuable than discovering a question and solving it then and there. Some such questions may be very difficult and the proof will be involved, but when somebody has conjectured and left it open, that kind of tells you that at least that person had put in a lot of effort and was unable to solve this. Okay, so the credit goes to Shep for actually solving this. And the proof, as I said, is a bit clever. I'm deviating a bit from how it is presented in the textbook Allen and Spencer. It's essentially the same idea, but kind of a lengthened version of it, so that it's more clear as to, at least this is my guesses of the sequence of ideas that would have led to this proof. Okay, so this is, I think there are something like idea 1 to idea 4. So let's start with idea 1. So firstly, this idea 1 makes sense only if you know that we are trying to prove it using FKG inequality. Okay, that's a negative point, but let's see, even if you want to use the FKG inequality, we should model this problem on lattices. But though this collection of all linear extensions of the given partial order P does not have a natural lattice structure. Okay, it's very difficult to define a join or a meet operation, though total orders are nothing but permutations, right? So a total order of a set in this case is actually, we can even think of it as a function from P to n, where n is the number of elements in P. This is a ranking of any total order pi. Let's say we can think of this, right? So this is pi of the first element, the first guy would be the guy which is mapped to 1. The second element in the total order will be the guy which is mapped to 2, and so on. So this is a function, and we have seen that functions do have a natural lattice structure. You can take this point-wise, pairwise, or component-wise less than or equal to as the order relation, and in that case the point-wise min and the point-wise max will play the role of meet and join respectively. But by taking the meet of two permutations need not give a permutation, because the bijectivity of the function will be lost most of the time if you take a meet or a join. Okay, so and this almost always it will be lost if we join. But then instead of taking this map to n, suppose you take this pi as a map from the elements of the poset P to a large codomain. Okay, so this M, I assume, is much larger than the size of the poset, right? Now you still have you have a collection of functions. Okay, for a moment, let's ignore how we are going to encode the fact that this will result in a permutation that will be a linear extension of P and so on. Like, this only building an idea. But if you have functions from P to a large codomain, then the likelihood that when you take the meet and the join are again going to be defined pointwise. Okay, and the partial order that we are going to do is, this is the order is defined pointwise, and this meet is defined as the join is defined as the pointwise max, and the meet is defined as the min. Now here also there are chances of collisions. You can always try to construct two functions which then will collide, but then we are not restricted to permutations. As long as you get another function, we are not putting a restriction of injectivity here, right? So hence it's okay even if while taking meet or the join, there is injectivity, even if it was originally there, it is lost. That's not directly of a concern here in terms of defining this as a lattice. Okay, so this functions from a poset to, in fact, functions from any domain to a set in which you have an order defined will turn out to be a lattice under this min and max operations. I think what you define, the codomain should also be a lattice. Okay, but now among these functions, if all the injective functions, if pi was an injective function, okay, among these functions, if pi was an injective function, then I can reconstruct a permutation out of pi. How do I do that? I sort this members of P in the order of pi of P, right? So you sort P according to the pi values. Okay, and not f values, pi values. So if you can sort P according to pi value, so here maybe there is no inverse image for 1, but among the codomain you identify the range, which are those points to which you have somebody mapped. Look at the smallest guy in the range, look at its inverse image. If there is no collision, that is the guy which will be the first element in the permutation. If there is a collision, then you put both of them in whichever way. By the way, this is an injective function, so there won't be any collision. So you rank guys according to their pi values, you will get a permutation. Okay, and if M is very large, as is the case that we are going to consider, then your injectivity is highly likely. Okay, we are still not saying it is guaranteed, but it is highly likely. In fact, at the end of the proof, we will take limit M goes to infinity, so that the non-injectivity probability tends to 0 and it will vanish, or the injectivity probability will go to 1. Okay. Now, if we pick a one-to-one function, if you pick an injective function pi in this context, from P to M uniformly at random, and do this sorting. No, we already do the sorting. We already said that we will get a permutation of the ground set of P, not necessarily one which respects P, but we will get a permutation of the ground set. But you can also verify that this is equivalent to picking a uniformly at random permutation of P. Okay, so I want you to verify this by yourself. Okay, in some sense you have to argue that the number of injective functions which will give you the same sorted permutation, on sorting which will give you a particular permutation, that number is the same for any permutation. Okay, if you can prove that, that means, this is a much larger domain, this has much more than n factorial members, but they are kind of equipartitioned. This is your injective functions inside of tau, right? But this is much more than n factorial, guys. But what we are saying is that this is kind of, equipartitioned into exactly the same number of, this will give one permutation pi 1, these guys will all give a second permutation pi 2, and so on. This will give pi n factorial. Okay, so each of the n factorial permutations result from the same number of injective functions in tau, and hence their their probabilities would also be uniform. One way to verify this is to verify it locally. Consider two permutations, say pi 1 and pi 2, which only differ by a swap. Okay, which only differ by a swap. Okay, now look at any function here, any one injective function here. Okay, I think I should not be using pi here. So for the permutation, let me use tau. Okay, no, tau is again a bad notation. Okay, sigma 1 and sigma 2. So for two permutations, let's say sigma 1 and sigma 2, which only differ in a swap, you can see that for all those functions, which kind of map to sigma 1, I can convert that to a function which maps to sigma 2 by swapping those two values corresponding to the same location where you can move from sigma 2 to sigma 1 by doing a swap. Okay, so sigma 1 to sigma 2 you do by doing a particular swap. Now swapping the corresponding values in these functions will change a function which would have given sigma 1 to a function which will give sigma 2 once you do this sorting operation. So there is a bijection between these two, which means the number of functions which when sorted give you sigma 1 is equal to the number of functions which when sorted will give you sigma 2. Now if that means both these are the same number, but now any two permutations are related by a series of swaps, right? So you can use this observation again, along the path which connects these two permutations in that auxiliary space, the space of all permutations, to show that any two permutations are going to be equally likely under this mapping. Okay, but actually, it is more instructive. Yeah, I wanted you to verify and then ended up saying most of what is needed. Okay, yeah, but as we already said, these permutations need not respect L. So now the next idea is to restrict your tau to only those permutations which respect, or only those functions, I should say. These pi's are functions. These are functions from P to a large codomain M. Right? By what do we mean when we say that a function respects P? It says that it is an increasing function of P. Okay, there's already a definition we know, but here somehow it's more intuitively clear if I say pi respects P. Whenever x precedes y in under this partial order P, the value of pi x should be less than or equal to value of pi y. These are the functions which we call as those which respect P. And now you see that if you do this sorting operation, this sorting according to pi values of the from a function pi which respects P, the order that you get, the linear linear order or the total order that you get is going to also respect P, and hence it will be a linear extension of P. Okay, this is the second key idea. So in order to focus our attention only on those functions which respect P, we use our mu function. Okay, so the mu in the FKG inequality, we will say that mu is 1 for those functions which respect P and 0 which 0 otherwise. So remember, mu is a function from, okay, by the way, what is our lattice here? Our lattice here is all those functions from P to L is all those functions from P to M with the usual pointwise less than or equal to. So meet is min, join is max. And this mu is a function, this is not a normalized measure, so I'll just call it R plus, it does not add to 1. Okay, so this is not a normalized measure, but we can easily normalize it by appropriately dividing it by mu of the whole set. Okay, so the mu kind of helps you focus your attention on only those functions in the lattice which respect P. Yeah, this is what we already said. Now sampling the restricted functions with respect to P. By the way, here also now even under this restriction, remember that the total number of functions from tau which map to a particular permutation has not changed, and this mu will put if two functions map to a permutation which respected p, then both of them would get a 1. Okay, so this mu only kind of changes the probability measure between one function which respects p versus another function which does not respect p. But among the functions which respects p, the total number of functions which get mapped to one such permutation which respects p is equal to the number of elements in tau which respects p and then maps to the, okay, I think I'm using too much words here. So what I'm trying to say is that if pi 1 and pi 2, if sigma 1 and sigma 2 are two permutations of p, right, then the number of guys in tau, sigma 1 under the sorting, the number of functions in tau which map to sigma 1 is equal to the number of functions in tau which map to sigma 2 under the sorting. And since sigma 1 and sigma 2 are both, and if sigma 1 and sigma 2 respect tau, then actually each of these functions will respect p, each of these functions will respect p, and each of these functions will also respect p, but this total number remains the same. So the uniformly at random property, the uniformness is not lost. Okay, so hence after sorting, every linear extension of p is equally likely. Okay, so now what we are saying is that if you consider the set of functions from p to a large codomain which respect p, and you pick one function from that uniformly at random and and get a permutation by sorting according to the pi values, this is equivalent to the random experiment of picking each linear extension of p equally likely. Okay, instead, I mean, here both models are correct. Either you can restrict your lattice, restrict your domain to this guys which respect p, or you can impose a probability measure mu, which we will later scale to be a probability measure. Yeah, that's anyway the next step. Okay, we will divide mu by mu of t to get a probability measure. So under this measure, it's equivalent to picking a linear extension of p uniformly at random. Okay, so that's the moral of this story. So this random experiment effectively picks a linear extension of p uniformly at random. Why do I say effectively? Because that's okay. Why do I say effectively? Because that's not exactly the experiment we do. Our experiment is on a larger domain and there is a sorting operation and so. Okay, now comes the third idea. We have to now verify the premise of the FKG inequality, but for this function mu, right, the mu has to be log supermodular. But we know that if pi and sigma respect p, right, these are functions, remember, these are not permutations. If pi and sigma respect p, then one can easily verify that both the join of pi and sigma as well as the meet of pi and sigma will also respect p. Okay, how do we prove that claim? It's very easy. Suppose take any two arbitrary elements x and y from the poset such that x precedes y. We have to show that under pi join sigma of x is less than or equal to pi join sigma of y. Similarly for the pi meet sigma. But what is pi join sigma of x? What is the definition of the join operator? That's the max of the two values, right? So it's max of pi x comma sigma x. But now remember, both pi and sigma respect p, which means since x precedes y, pi x is less than or equal to pi y and sigma x is less than or equal to sigma y. So both the arguments inside the max function kind of dominate the corresponding arguments in the previous line. So this max value can never go down. So this is less than or equal to max of pi y sigma y, which is nothing but the join evaluated at y. Okay, so the join respects the order among x and y. Similarly, the meet will also respect the order. Again, this minimum and this minimum, pairwise these two arguments dominate these two arguments, so the minimum cannot go down. Okay, so the join and the meet will also be functions which respect P. In fact, it is because of this reason that instead of using mu, I can actually restrict my whole lattice just to permutations which not permutations, that's a mistake, just to functions which respect P. Okay, even we can actually redo this proof where mu is just a constant function 1, but then the lattice is shrunken only to contain those functions which respect P. Okay, but we will follow this because in the textbook I don't want to deviate too much from the textbook, because I want you to go back to the textbook and verify that what we are doing here matches with what is written there. Okay, but with this property we have ensured that pi and sigma, any two permutations in tau, will satisfy, or we have ensured that mu satisfies log supermodularity. Why? In order to show log supermodularity, this is the inequality that we have to prove, that mu of pi, mu of sigma is upper bounded by mu of their join times mu of their meet. But now remember, mu is a 0-1 valued function, right? Mu only takes either 0 if the function does not respect P, and 1 if the function respects P. So the only case where this can go wrong is when both the left hand side terms are 1 and one of the right hand side terms is 0. That's the only way this inequality can go wrong for a 0-1 function. But yeah, so that's what we are saying. The only case it can go wrong is when the left hand side is 1 for both, but one of them is wrong. So which is not going to be the case, because if this is 1, that means pi respects P. If this is 1, that means sigma respects P. We just showed that in that case pi, this also will be 1 because the join respects P. This also will be 1 because the meet respects P, right? So when this is both 1, this would never be 0. Hence, this verifies the log supermodularity condition for mu. That finishes idea 3. Okay, now idea 4. Okay, this is probably the most clever idea in my opinion, right? Now, in order to apply FKG inequality, we also need these two increasing functions f and g, such that finally, this expectation under mu of f, this is nothing but expectation under mu of f, turns out to be the probability of our first event E1. Remember, E1 was the event that your x would be placed before y by the linear extension. And since this linear extension is going to be obtained by sorting this function pi according to the pi values, or the domain according to the pi values, this is equivalent to saying that pi of x is less than or equal to pi of y. Similarly, I want g to be defined in such a way that the expectation of g turns out to be the probability of E2, or pi of x less than or equal to pi of z. Okay, and thirdly, we want the correlation or the joint expectation of the product fg to be equal to the probability of E1 intersection E2. So we have to now cook up two functions which will satisfy these conditions, and the functions have to be increasing. So if you forget for a minute the requirement that these functions have to be increasing, this, though it looks kind of a if you haven't seen this before, then this will look like a bit of a challenge. How do you find such functions? But now, if you with some experience in working with expectations and probability, you actually know that expectation is a much more general quantity than probability itself, in the following sense. If I want to write the probability of some set A in terms of an expectation, I can always write it as this is probability under some distribution mu. I can always write it as the expectation of the characteristic function of A. What is the characteristic function of A? It assigns 1 to all the members of A and 0 outside of A. And you see that the probability of A turns out to be the expectation of the characteristic function of A, right? Why? Because this is equal to sum of all A in A, mu of A times 1. And this will be 0 I can also write plus sigma A not in A mu of A times 0. So this term does not contribute. This is the only term that contributes, and this is nothing but the probability of this entire set A. Okay, so yeah, so it is expectation. In fact, this is what is known as a zeroth moment. The usual expectation, the expectation of a random variable, if you consider it as the first moment, this is, so some people even call probability as a zeroth moment in this sense. Okay, so any probability you can easily write as an expectation by choosing expectation of which function. The function you have to pick to be the characteristic function of that set. Okay, so by the way, this is a very, very handy trick to remember on how to express probability as an expectation. So in this sense, proving the Kleitman's non-uniform version from the FKG inequality is just a single line, because FKG inequality talks about positive correlation among any two increasing functions, and in order to prove Kleitman's inequality, we only have to show that the characteristic functions of two events are increasing under this context, right? By the way, a characteristic function under this usual subset or this power set lattice is always increasing, right? Because if A is a subset of B, then the characteristic function, if you evaluate, right, take any characteristic function of another set S, you can see that the characteristic function evaluated at A will be less than or equal to the characteristic function of S evaluated by B. By this I mean you take each element in A and check its characteristic function value, which means you are checking whether it is a member of S and adding up all those, right? So this is nothing but the number of elements in S intersection A, and this is nothing but the number of elements in S intersection B. Since A is a subset of B, this is going to be satisfied. So under the power set lattice, characteristic functions are always increasing functions. So this is a very useful technique to know in general. But in this context, we really need this idea 4. This wouldn't qualify to be an idea, because this is a very common tool in the arsenal of a probability theorist, right? But here the problem is that we are not working in the power set lattice, and hence characteristic functions need not be increasing, right? So for example, by the way, this is this natural choice. You can define your f to be 1 if f respects if already pi will respect, we are only bothered, we are giving probability measure, non-zero probability only to those functions which respect p. But this is an additional constraint. We set f to be 1 or the characteristic function of those functions which, in addition to respecting p, also satisfy this inequality that pi of x is less than pi y. Okay, so this is in some sense the characteristic function of the event E1 that we are talking about. Similarly, this characteristic function of the event that x is less than or equal to y. Similarly, g would be the characteristic function of the event E2. Okay, that x is less than or equal to z. But unfortunately, as we said, f and g are not necessarily monotone. We can actually find two functions, pi and sigma, from tau, such that both of them respect p. Pi satisfies E1, right? That pi value of x is less than or equal to pi value, and sigma point-wise dominates pi. Sigma point-wise dominate pi, but sigma can fail to satisfy this inequality between x and y, right? You can easily construct that, or you can look at this example. I'm just taking this 1, 2, 3, 4, 6 under divisibility as the poset. So this red dots indicate pi, which is where you actually assign, these are the pi values, right? 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, 6 is mapped to 5 for a reason. Okay, I'm allowed to take m large, so I'm allowed to do this. But now consider another function sigma, where I'm just changing the value at 2. 2 is now mapped to 4 instead of 2 as it was earlier, right? Now you can see that sigma point-wise dominates pi. Sigma also respects p, because none of the relations originally in p are affected by this change. But you see that sigma does not obey this property that sigma of 2 is less than or equal to sigma of 3. So this is why the characteristic function is not an increasing function, right? So even though pi precedes sigma, the sigma value, it is outside the set. This actually means f of pi is equal to 1, but f of sigma is equal to 0, and hence, and because of this condition, this means f is not an increasing function. So this crisis is what calls for the idea 4. Okay, idea 4 stems from this issue. Okay, so the idea is to restrict tau to only those functions which assign x to m by 2. Remember, though this Xyz theorem, you can pick any 3 xyz while doing this proof. Okay, at least from this point onwards, when we are starting to define f and g, we are fixing 3 points x, y, and z in your partial order P. And in fact, from this point onwards, this dependence, we are actually going to go back to tau and even change tau. So it is actually better to assume that your x, y, and z are fixed before you start the proof, and then you restrict your tau to only those functions where the x is assigned to m by 2. The midpoint, we can even assume that m is a large even number. Okay, so we need to fix x before we reach this point. Okay, yeah, and again, so this is the tau prime that I'm talking about. It is all those functions from P to m such that f of x is equal to m by 2. Remember, x is not an arbitrary quantity. X is the particular guy which appears in both the events E1 and E2. It is that particular x that we are talking about. Okay, so that guy is fixed to m by 2. Now, if you restrict to tau prime, then you can verify that the characteristic functions of E1 and characteristic function of E2, which is f and g as we defined, are both monotone functions, right? Because the position of x is kind of logged. Now, if if one function respects this E1, like its pi value for this is your x and this is your y, and this is your function, let's say pi. Now anything that is pointwise above pi, since x is not allowed to move, it is fixed at m by 2, x is fixed at m by 2, y can only move upwards because the next function we are only talking about functions which are above pi in this case. So this can only move up, but it would still satisfy E1, right? So the characteristic function will assign 1 to that also. So this shows that f is a increasing function in this domain. Similarly, the g is also an increasing function, right? So restricted to tau prime, that's the key thing. Restricted to tau prime, both f and g are increasing functions, right? Now you should probably go back and visit all these steps and say that whatever we said earlier would also true. The meet and join is still a function which is in tau prime, right? So it is a lattice because the min and max, if you take at the value of x, it would still remain m by 2, and hence the result is also a function in tau prime. And similarly, mu will remain log supermodular, but anyway it was log supermodular in the larger set, so it will remain log supermodular here also. Maybe, but it's a good time to go back and see that all of this are satisfied. Okay, so yeah, we have to go back and check if everything is okay, and hence we are ready to apply the FKG inequality, E mu of Fg greater than or equal to the product of the expectations. But now, since f and g are characteristic functions of two sets, so yeah, what is the characteristic function? If you take a characteristic function of a set A and multiply it with a characteristic function of another set, you actually end up getting the characteristic function of S intersection T. Okay, so this Fg is the characteristic function of E1 intersection E2, and hence this expectation is nothing but the probability of E1 intersection E2. This is easily the probability of E1, and this is the probability of E2 because F is nothing but the characteristic function of E1, G is nothing but the characteristic function of E2. So we have proved the Xyz theorem that the probability that X will precede Y as well as Y will precede Z is greater than or equal to probability of product of the probability of the individual events if you pick a linear extension uniformly at random. Okay. This remark is something which I had already said. We can in fact choose to work with the lattice, which is just all those functions which respect p as well as x is mapped to m by 2. Take m to be an even number and set mu as a uniform distribution on this. Okay, work it out in this way. Working it out will probably help you appreciate the proof better. But we cannot restrict to injective functions in this set, because then it is not a lattice. The meet of two injective functions need not be an injective function, right? So we have to still argue that take limit m tends to infinity, and then the probability of being injective goes to 1. So in the limit we get what this conclusion kind of holds. So here there is actually a small jump because of the non-injectivity possibility, but for a very large m that is negligible, and in the limit it will vanish. Okay, so that proves the Xyz theorem, and I think we will conclude our discussion about correlation inequalities with this. So remember, the name correlation inequality probably makes most sense with the FKG inequality stated in this form. Okay, that it's about saying two functions are positively correlated if both of them are monotonically increasing and the underlying probability measure is log supermodular. Okay, thank you.